Hello, friends. Welcome back. It's good to see you. Yeah. It is. It's finally fall. Still wearing summer clothes, though, as I will be until I absolutely have to put on pants. I hate pants, so I will continue wearing my shorts as long as humanly possible. So it's pretty nice outside today, right? Yeah, by now. It's a little chilly this morning, but in a good way. Apparently my PowerPoint has lost its will to live again, though. There it comes back. So good. So we are hopefully going to wrap up CFA today. If not today, then Monday. Anything that you want to chat about before we dive into review? Any questions, thoughts, comments? No? All right. Is it hot in here? No, she's fanning yourself. Did you just run here and you're exhausted? Okay, you can go bring the fan over if you want. Yes, I had to walk 5 feet from my office across the hall, so I'm very spoiled. Those of you who are commuting from JRP or Fraser or all those places, thank you for making the trek down here. Or Kansas City, as it were, right? But not on foot. Yeah. So we've been talking about assessing fit in CFA, right? Fit is all about match. It's the idea of you've got the right answer, you've got your data. You've got your item means, variances, and covariances. You know what they are. How well can your model approximate them? How well does that pattern of covariance map onto the prediction that a single factor would make, or 2 factors, or 3 factors, or whatever your prediction happens to be? You don't have to start with 1. If you predict 2, you can start with 2. However, it's most useful in terms of troubleshooting to narrow the analysis down to just 1 factor at a time. Because think about if you have, say, 3 factors, 18 items, which is what the full forgiveness scale is. We're looking at 6. You have an 18 by 18 matrix to troubleshoot. If your model doesn't fit, that's a little tricky. It's hard to get all of that to work at the same time. Whereas if I start with just 1 factor of 6 items, once I get to the point where I know that works, I test the next one and the next one. Then when you put all 18 together into a single model, if that model doesn't fit, you know the problem isn't within the factor, it's the relationship of the items across the factors. And so it helps narrow down the possible realm of your troubleshooting. So I'm starting with 1 factor, as I always would be, but if your theory specifies that you have more than 1 factor, that's okay. I just recommend starting with 1 so long as your model is testable. So some of you have come up to me and talked about your data. A few people have factors that have only 3 items. I think I've talked to a few people like that. You have that. And what did I tell you to do about that? Combine them. So if you have 2 factors that each measure 3 or fewer items, put them together into 1 model. That way the model is testable. That's the exception to the 1 factor at a time rule. Otherwise, if you've got 4 items or more, 1 factor at a time helps you troubleshoot just that set of items at a time. So fit is all about match. And whenever you tell your readers that you've done any kind of structural equation modeling or confirmatory factor analysis or path analysis, they immediately want to know if your model fits. Now think about this from the perspective of what you used to know. Has anyone ever asked you how well your regression model fit? Not a thing, right? Why isn't it a thing? Well, the answer key is you have 1 y, right? A regression model has a single outcome. You know what its total variance is because it gives you a residual variance. There is no room for misfit. There is no pattern that you're trying to approximate. When people say fit in the context of regression, they're thinking R-square, which is how good your model is at saying why some people have a higher y value than other people. That is not fit. That is effect size. So what we're doing up to this point is not the same thing you're used to doing. It's not about predicting individual differences. It's about describing the pattern of relationship as theorized by how many types of individual differences there are. So is this correlation pattern across your items due to 1 thing or due to 2 things? Does each item contribute equally? Are some items better than others? That's what we're trying to figure out. At the very, very end of figuring all of that out, we will get the chance then in an SEM context to figure out why people have different individual differences, to be able to test hypotheses about how the constructs relate to each other. So matching patterns is the name of the game thus far. So we talked about 4 steps of model fit. We've been through 2 of the 4. So just picking up on slide 46 here in lecture 4. Global model fit. How well does your total overall predicted item covariance matrix match the one from the data? And this is the idea of whether or not your model, Gesundheit, is significantly shorter than the best model. So here's my crappy diagram. Here's H1. This is the height of the data. So this is the best case scenario. What we're going for is an HO, our specified model, that is not different in height than H1. It will never be taller. It can only be as tall as. So we're going for not different. And we get a chi-square test that is the difference in -2 log likelihood between H1 and HO, and that shows up on your output always. If you pick a new HO, you would have to test that HO against your previous one. The only comparison that will show up on the output is still your HO versus this H1. Another comparison that shows up on the output that you can disregard in most cases is the worst possible model, this null model, against H1, because that has nothing to do with what you told M+ to do. The null model says there's no covariance whatsoever. The H1 model lets each covariance be whatever it wants, so there's no prediction happening between those two. So the next step then, local fit, helping diagnose why your model doesn't fit or making sure that you're not missing any problems. Do you remember this idea? The report card analogy, maybe? I'll get that out. There we go. Both of these report cards would give you a grade point average of 3.0. How you would go about trying to improve that grade point average would matter drastically as to which report card you're starting from. So the idea of local misfit is that you really hope you see something like A, where there is a very specific cause that you can then try to fix. Unfortunately, a lot of the time it looks more like B, where there's just sort of misfit all over the place, but there's nothing that's big enough to be the problem of misfit. But the idea of local fit is to look at the difference between the covariance matrix that you predicted with your model and the covariance matrix in the data and look at the specific differences. So I did this for you in Excel. Let me get that back out again to show you how that works. So here I'm working in a correlation matrix. I keep switching back and forth between correlation and covariance because the ideas are the same. The unstandardized solution predicts covariances. The standardized solution predicts correlations. They're algebraically linked. So you can talk about one and the other will hold as well. So if we start with the correlation matrix in the data here, that's what the answer is. That's H1. Here's the one that my single factor model for my 6 items we've been talking about predicted. And then these cells down here are the differences between what the model says and what the data say. So these are discrepancies in correlations. And we note in the comment here, variances are always perfectly reproduced so long as each item gets what? Its own error variance. The error variances fill in the difference between whatever the model says the variance should be and whatever the rest of it is. Not shown in the picture, because it's almost always not a problem, are the item means. So long as each item gets its own what are the item means perfect? Intercept, yes. So that leaves the only other item parameter to worry about, the loadings. It's all about the loadings and how well they recreate the pattern of covariance and correlation, where the unstandardized loading recreate covariance, standardized loadings recreate correlation. So I color-coded this using my favorite trick in Excel, conditional formatting, so that the differences jumped out at us. And so this is more like report card A, where there's really 3 problems here. Items 2, 4, and 6 are more related than what the model said they should be. Now, how do I know that it's more? Because this difference in correlation between predicted and observed is positive. The correlation in the data is higher than the correlation the model said. So they're more together than what a single factor model would imply. So there are various ways to fix this problem. And M+ is going to pick up on this discrepancy and suggest ways to fix it. So that's what you get when you ask for residual as an option. So on the M+ code on the very first page of example 4 here, just to tell you where I got this stuff, STDYX gives you the standardized solution. Residual gives you those discrepancies. It's the difference between predicted and observed in a standardized metric. And mod indices, those are modification indices. Those are suggestions, things you can add to the model that will reduce the discrepancy between HO and H1. And I set it up to report only suggestions that would improve the model at p less than 0.01 for 1 degrees of freedom. That's what that 6.6 comes from. That's the chi-square value. So we get, then, from the residual output, right here, this is page 9, this table here, normalized residuals for covariances, correlations, and residual correlations. So normalized means it's taking, there's the formula up there, the observed difference minus what was predicted and divided by the standard deviation of the observed. So it's trying to take those discrepancies and put them onto like a z-score scale so that you don't have to know what the scale of the variable is anymore. You can look at this sort of standardized version. And the same 3 problems that jumped out at us in the correlation matrix then jump out at us in this metric as well. So anything above 2 to 3-ish is indicative of a problem. So the ones that are positive mean that in reality these items are more correlated than predicted. The ones that are negative mean that they are less related than predicted. They don't want to be part of the same factor. Negative ones are harder to troubleshoot because that implies that you have to think about another factor to be part of your model. Whereas positive ones, you can add extra things to soak up that extra unpredicted correlation. So what we had done then is split the positive and negative items into 2 factors. I did that because this pattern of relationships among the 3 suggested that that would be a reasonable thing to do. And then we then saw that it fit better than our previous HO model, and even though it didn't fit perfectly via the chi-square test, all of the other fit indices suggested that it fit very well. And then in looking at the residual output, nothing jumped out at us in terms of what should happen. So, and I think that was where we left off. So, questions on any of that? Or anything you want to hear again? Now instead of later, right? Yes, sir. When you're doing growth modeling. So a special case of these models is when you're trying to indicate, say, like linear change over time. You would have one factor that's the intercept and one factor that's a slope. And rather than letting the model estimate the factor loadings, you code them with the value of how much time has passed That would be a column in your data set normally. And the whole idea of the growth model is that the factors should capture all of the reasons for change over time. So you would actually fix all of your intercepts to 0. That way, all of that difference in mean goes up to the factor level. And likewise, the random slope factor is supposed to account for differences in variance over time, because if people grow differently, they spread out. And so you would fix the residual variances to be the same for each item, which is actually a time point, so that the slope factor then can take over and predict that heterogeneity of variance. You could, but then that means that everything is fair game. So if your model doesn't fit, that could show up as a misfitting mean. It could show up as a misfitting residual variance or misfitting covariances between residuals, because you're saying that after accounting for the factors, the time points are independent. It still may be the case that time points that are closer together are more related. And so fit assessment is relevant when you're doing growth type modeling, with two catches. One is that it's only possible to do fit assessment in this context when you have balance time, when everybody shares a common set of occasions, because that's the only situation in which you have one covariance matrix to come back to as the right answer. And let's see, I think I lost the other one. That's the only time. It's gone. I think I answered the question, though, without rambling too much. Okay, good. Yeah. Oh, I know what it was. I just remembered. In that situation, this little null crappiest model ever is actually the wrong one, because that null model gives you separate variances over time and separate means over time, whereas what you would really want is what I would call an empty model, where the means are all the same and the variances are all the same too. So a stricter version of null would be needed to get CFI and TLI correct in a growth model. But that's my other class. That was last year. That was so 2017. Other questions? All right, then let's talk about what to do when your model is broken, because you know it's going to happen to you. So, ways to fix your model. That's what we're talking about here. Slide 53. Anything that you add to your model, you want to see if your model gets better, if fit improves, if the difference between your HO and H1 saturated perfect gets smaller. And in other areas of statistics, you will do something called a -2 log likelihood difference, or a likelihood ratio test as it's known more generally. In this case, because we're using robust maximum likelihood, there's an extra step to the calculation involving the scaling factors. So you can't just take the straight difference in log likelihood and multiply it by -2. You have to use the extra formula. And so here's where they describe it on their website. In the example spreadsheet that goes with this, I have a tab called Model Comparisons, Table 2, and I've built the spreadsheet for you. So you just have to enter these three things: the model log likelihood value for the to-be-compared models, their scaling factors, and their number of free parameters, meaning the number of things you've estimated. And then the rest of this, as you can see by the heading Calculated, gets calculated for you. So this scaled difference in -2 log likelihood, that's your chi-square. The difference in degrees of freedom, or the number of things you've added, that's the degrees of freedom for this comparison. And then the chi-dist function will give you an exact p-value for that chi-square or degrees of freedom combination. So there's the formula. You can see why I decided to build a spreadsheet. I don't want to try and do this with a calculator, right? It's annoying. But the basic idea is that you have the difference in the log likelihoods as a function of the difference in parameters. So the difference follows a chi-square distribution when you multiply it by 2. That's where the 2 comes in. So you get used to seeing these numbers as an easy reference. If you've added one thing, a significantly better chi-square, better model by the chi-square would be 3.84. On alpha, 0.05. If you've added two things, the cutoff value is 5.99, and so on. Keep in mind that in testing differences in model fit, you want to be able to think about the direction of the comparison relative to what you want to know. So if you're trying to make your model better, you are trying to add parameters. If you add parameters, your model can get better or not better. So if you try to add something and it doesn't help, that shows up as a non-significant chi-square for the difference between what you had and what you have now. So I would phrase that as not better, not an improvement. If you have a significant chi-square, then you do have significant improvement. So my old model was worse than my new model. My new model is better than my old model. So these are the comparisons that you have to do, because now we're talking about different kinds of HO models that you specify. You have to be able to figure out whether what you've added relative to what you had before makes it better. So you're inching your way closer to the H1 model here. Question?
Is there an indication of how much better, or do you make things, is there a point at which like adding more things, if it's not making it that much better, is not preferable, or?
Yeah, I mean the formal way to test that is the likelihood ratio test. Yeah. If it's significant, it's better. But you also look at changes in the other fit indices, CFI, RMSEA, and so forth. RMSEA in particular, it's ofteness divided by the number of parameters left, and so it can get worse because you keep adding things and it's only a marginal improvement. So the formal way to test it is the -2 log likelihood difference, but you also do want to pay attention to the other indices and make sure that you're not, I guess, overfitting from that perspective. Other, yeah, yes, please. You can do two parameters together. So as an example, if you go from a 1-factor model to a 3-factor model, then you're adding the 3 covariances between the factors, essentially, at the same time. Yeah, I mean, you can do as many as makes sense. Because if you add a new thing, it might be one thing or it might be a set of things. Like if you add a new factor, the new factor may have extra loadings and that kind of thing. So yeah, so long as they're nested. Other questions? So other kinds of comparisons that we would be interested in are phrased from the opposite perspective, the idea of simplifying the model. So the test of model fit, when you compare HO and H1, you think of this way. You know H1 is best. Your objective is something simpler, meaning fewer than all possible parameters spent, that's not worse. So simpler means you have fewer loadings than you have covariances that they're trying to predict. Another instance in which we want to see if simpler makes it not worse is when you're putting in constraints. So if you want to test whether or not your items have equal discrimination, that your items are equally good, the way to do that is to force them all to have the same loading, to share a loading. And then you can compare the model in which all the loadings are separate to the model in which they share one. That's a simplification. Your goal would be to say not worse. If the model fits not worse, meaning a non-significant chi-square after constraining all the loadings to be the same, that's evidence that your loadings, your discriminations, are equal across your items. They all work equally well. Another instance in which we'll do that version is measurement invariance, or measurement equivalence. The idea that your instrument is working the same way across different types of people. That starts out by letting each group have its own everything and slowly, stepwise, forcing all of the groups to share parameters. And if your instrument is working the same way, you should be able to make them share everything and have the model fit get not worse as you go. So it's a semantic distinction in some ways, but I see people mess this up where they say things like, I added this and it didn't get worse. And it's like, no, that can't happen. It's backwards. So when you add things, it's better or not better. When you subtract things, simplify, it's worse or not worse. Just as a side note here, sometimes you will end up in a situation in which the null hypothesis of 0 doesn't work for a parameter. So for instance, if you're testing whether you need 2 factors or 1, what that actually amounts to is testing whether the correlation between your factors is something different than 1, under 1. And because the correlation of 1 is on the boundary of what it can be, the chi-square that you should use is not the actual chi-square for 1 degree of freedom. It would be a mixture. So you see this in testing variances in random effects models or multi-level models. That just means that if you are testing this hypothesis, technically speaking, your critical value for a chi-square should be 2.71 instead of 3.84. Very few times will you be on the boundary where that thing would matter, but I just wanted to put that in as an aside. So the chi-square of 2.71 comes from using an alpha of 0.10 instead of 0.05, because your correlation can't be over 1. It can only be under 1. So you're missing the other half of the distribution for what you would be testing it against. So non-nested models. Sometimes the models that you will be compared will not be nested in the sense that you're not adding or subtracting, you're just moving things around. So for instance, if I'm not sure which factor an item should go with, I can try it on factor 1, and then I can move it to factor 2. Those models will have the same degrees of freedom. So I can't do a likelihood ratio test. I can't do -2 log likelihood. What I can do, though, is look at values that are based on -2 log likelihood, which is known as information criteria. And if you've seen this in logistic regression, you'll see this in multi-level modeling, you'll see this in anything that uses maximum likelihood to estimate parameters. AIC and BIC are the most commonly reported. There's many other variations on this. Smaller is better. The reason that smaller is better instead of bigger is that what goes into this is -2 log likelihood, not log likelihood. Why they do this to you, I don't know. I just think job security. That's the only reason why they would give it 2 backwards things. But other programs like Stata do the same thing. They give log likelihood, and then they give these things in -2 log likelihood form. The downside with these is that there is no cutoff. These don't have distributions. There's no p-values. So smaller is better. How much smaller? Smaller. It's kind of dissatisfying. You can also look at all the other fit indices, and that would be something else that you could report if you wanted to make an argument as to which version of your model is preferable. So what do you do then when you have these extra patterns of correlation above and beyond what your factor model says? So in our example, I had one factor that I fit. Items 2, 4, and 6 were more related than what the factor said. Here are the options that I have for fixing this. The easiest and potentially most hardest to defend is error covariances. So error covariance, residual correlation, residual covariance, all of those words mean the same thing. You literally just say, this item gets to be correlated with this item in the code. So it would look like, let's see, I don't even need to draw it. You would end up with referring to the item, the word with, referring to the item again. When you refer to an item, you are actually referring to its variance or its residual variance, depending on the model. If the item is an outcome, you are referring to its residual variance. If it is a predictor, you're referring to its variance. Accordingly, when you say item with the other item, what you're actually asking for is to estimate a residual covariance, letting their residuals be related. So whatever is not the factor is related across the items. So it's an implicit multidimensionality that you're putting in there, but you don't know why it's there. And you don't have to. So it's a very atheoretical, data-driven kind of thing, and that's why people don't like it, and you have to defend it. So you will see in M+, lots and lots and lots and lots of these suggested. And when you change your model, different ones might get suggested. Do not restart. No, 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 no. This happened last time. So my computer is not under my control. Someone else installed all this crap on it for KU, and it decides to restart itself sometimes without my permission. So we'll see if this happens again, but I will apologize in advance if it does. So situations in which you could probably defend an error covariance. When you have something overly in common, but is still relevant to the construct. So on the example we're going to see in just a minute, in your textbook, the author had a scale measuring anxiety, and 2 of the items referred to like giving a speech or something that had to do with social anxiety specifically, and those were the only 2 items that looked like that. Well, those 2 items wanted to be more together. Not surprising. So an error correlation based on that common content could be justifiable. If it's common wording, so things where everything is worded one way except for 2 items, those 2 items may be more related. Likewise, if you have all items that are positively worded except for 2 are negatively worded, those 2 may want to be together. So you should be able to anticipate, based on the content of the items, which ones might need error covariances, and that will give you some ground to stand on when you try to defend any of these modifications to your model. So it's unaccounted for multidimensionality. There's something else besides the factor that is responsible for creating the pattern of correlation in these items. If you have lots of these problematic pairings, particularly if they pair together, like in our case it was 2 with 4, 4 with 6, and 2 with 6, that's a dead giveaway that you need another factor. The question is whether it's going to be another content factor or a method factor. Let me see. Yeah, so here are the pictures I wanted. I don't have to draw them. He already did. So this is from your textbook. So here are four items that, yeah, so social interaction anxiety and then public speaking anxiety. Sorry, I misspoke the words in the circles a little bit. Here's the thing, folks. All 4 of these models are statistically equivalent. They're the same. Yeah, I love the head shake, Mayumi. Like, what? I know, right? Because they make very different statements, theoretically, but they're the same. So the middle one here is the most direct way to solve a problem where these 2 items are more related to each other than is predicted by this factor. You just let them have an extra relationship. It literally plugs the hole in the correlation matrix with however much off you have from the model. It just lets the residual correlation be that. That way the discrepancy between data and model is minimized. It's gone. Ta-da! Alternatively, you could do something like this on the left. Fit a second factor. Now I have a factor of public speaking anxiety and a factor of social interaction anxiety. This model is estimable and testable so long as these 2 things have a covariance. So even though this one only has 2 and it's locally under-identified, it can borrow information from the rest of the items in order to make this thing work. So when would you do this? Well, think about the other constructs that are going to go in your model. Are you interested in seeing if public speaking anxiety predicts whatever uniquely in addition to social interaction anxiety? Maybe. You could be interested in that. So you need to operationalize that extra relationship as a factor so that that factor can then go predict other stuff or be predicted by other stuff. Whereas the error correlation, you're just kind of trying to bury it. Like, I'm controlling for it. I don't really care. So that would be more appropriate when it's a nuisance relationship, like something like a direction of wording or common stem as opposed to common content. Taking this 2-factor model, you can also fit what is known as a higher order factor model. Don't you dare. Don't make me start drawing. No, no, no. It's pausing. Maybe it heard me. Yeah, I know. I know, like, your phones hear you, right? You get advertisements for things that you've been talking about, and it's really creepy. So why can't I use that power for good? Yeah, I've read some. Yeah. Okay, computer, if you're listening, I'm going to recycle you if you keep this shit up, all right? How's that? Tough love? Speaking of which, we're in the great basement cleanout of 2018 at my house, and I have a computer equipment graveyard down there. Does anyone need a keyboard? Or like a million extra cords for monitors or power adapters? If there's any like random computer equipment you need, please talk to me because I may be able to help you. Yeah, I'm serious. Okay. Oh, it's trying to update Office. I see what happens. Okay. Well, let me see if I can get through this without it actually updating. Back to my picture. There we go. No. I'm warning you. Okay. Try to talk quickly. So, this thing on down here, bottom left, that is a higher order factor model. What it's trying to do is say that those two factors are themselves indicator of another common thing. So now we're back to what you originally wanted as general social anxiety that incorporates sort of all of these things. So there's someone's general social anxiety, which manifests in two different ways. There's social interaction anxiety and public speaking anxiety. And then each of those then causes the way they answered those particular questions. That's the idea. However, the reason that each of these two-factor models is equivalent is right here. This higher order factor of general social anxiety, how many indicators does it have directly underneath it? 2. What did we learn about two-item models? They're not identified. So the only way to make this work is to fix both of these loadings to 1, which is saying these things are just correlated. So there's one correlation between these two things, therefore there can only be one loading. So this higher order factor right here is not testable. It's not even estimable until you force these loadings to be equal. And at that point, all you're doing is taking this covariance between the two and giving it its own circle and its own name. That's what you're doing. Can you guess how many of these lower order circles we would need to make this higher order testable? 4. Same rule as before. So when would you do this? Well, you may end up doing this in your dissertations. This is a very common problem, where someone refers to their construct, such as, I'm going to look at how social anxiety relates to blah, blah, and blah. And then you run the factor analysis on your items, and you find out that they're multidimensional. And you're like, well, I don't want to have 5 kinds of social anxiety. I just want 1. If these things are very highly related, then you would run into problems in letting all the types of social anxiety be in the same model because they're collinear with each other. It will make it difficult to show unique relationships of any one. So if what you still want to look at is social anxiety in the big picture, fitting a higher order model like this is a way that you can preserve that idea while still acknowledging the fact that social anxiety is itself multidimensional. So to try and get back to the one thing you wanted to begin with, this is a solution. Yeah.
So my survey, so I have like 57 moral violations in it. If by chance, well, like half of them have to do with boys committing moral violations, half of them have to do with girls committing them, or like some of them are in schools, some of them are adults. So I'm not necessarily interested in that, but would that help my model if I did something like this?
It depends on whether you think of moral violations by boys versus girls as two constructs, or you just want to control for the fact that you've got gender differences and that's not really part of your story.
Yeah, it's not really part of my story.
Okay, you just want to make it go away?
Yeah, I actually have evidence that there wouldn't be a difference.
Okay. So what you want is this thing over here. This model on the right. So this gets described using a couple different terms. He calls it a method factor. I call it a method factor. It's also known as a bifactor model. The idea is that it's two factors, but one is like the slop factor of things you don't want to know, and the other's the pure good one that you wanted in the first place. So in this case, every item still loads on the original social interaction anxiety factor. But the two items that have that extra correlation load on a second factor. And the second factor is not related to the first. So what we have here then is like factor, not the factor, and then more not the factors in the residual. So this is like not the factor for a particular reason, and then the rest of the not factors that are unrelated across items. So I drew a picture on the board. Let's see, who was I talking to? Was that, yeah, the Ouijan. I get it? Close enough? Yeah. Okay, you say it. It almost sounds like there's a W there. Ouijan? Maybe I'm just hallucinating. I'm sorry. I'm really trying to get everyone's name right. Thank you to all of you for none of you calling me Lessa, by the way. That one drives me nuts. It's like it's not even phonetic. Okay, I need a new picture. How do I make a new one? Menu. New. There we go. All right. So you had a survey about financial something. What was it? Financial well-being. I'm drawing in paint again here. Financial, that's a W, and that's an F. Financial well-being, right? And so we've got the items. The boxes are going to be pretty bad, I'm sorry. Looks like Huey drew them. He's very good at doing H's, though. So, there we go. And some of the items were positively worded, right? So I'm drawing plus signs in here. And some of the items were negatively worded. So the text that she showed me describing what these people had done is fit a bifactor model. So there's another factor down here that is basically a positive factor and another one that's negative. So then the positively worded items get those loadings. The negatively worded items get those loadings. So each item has a content loading for the thing it was supposed to measure and an extra effect of being measured in a certain way. That's the idea. Now, is this model identified that I just drew with 4 items? No, you're right. Yeah, do make that face. What will M+ tell you if you tried to do this? Not identified, check your model, check your standard errors, do not pass go, no, 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 no. You need way more than 4 items to be able to differentiate these 3 things. I didn't have room to draw them all. But this, that's another thing that you could do. So then you get into questions of interpretations. Well, how do you know that this one up here is the good one and that these ones are just the crap left over? Well, if these are really just about the direction of the wording, you should be able to constrain all of the loadings for this one to be the same and all of the loadings for this one to be the same, because with respect to just item direction, they should be interchangeable. So this is where you can put constraints and see how well those constraints make the model not worse in order to justify your interpretation of what exactly these circles mean. So you want that one, I think.
But like I have like half of them would be with boys, half of them would be with females.
So you have a male factor and a female factor.
Okay, yeah.
just like this is positive and negative. It'll be almost exactly the same. The key to making this identified is that the factors are uncorrelated. Otherwise, you get into an exploratory factor analysis situation. Yes?
Wait, so his would have 3 factors, right? A main factor, and then there would be men and women.
Yeah, this is an M, and this is a W.
So like in your method factor 1, there would be a third. But it's not going to look like that, though.
Moral whatever is at top?
Yeah, say physical harm.
Physical harm, okay. And then there is extra commonality in how people respond because the story is about a woman?
Yeah, or the black woman committing moral violation or
yeah, and then extra relationship because of how they respond to this. So these are method factors that are supposed to soak up that extra correlation in a more parsimonious way than letting all the women items be correlated for their residuals and letting all the man items be correlated for their residuals. Question? No. They should not be, because the only reason for correlations across should be up on the top, the construct. This is also sometimes called multi-trait, multi-method, if there's multiple factors on the top and then multiple method factors on the bottom. Your textbook has a chapter about that I didn't assign, because that data doesn't pop up very often. As a foreshadowing to what we're talking about next week, when you're fitting models for categorical responses, so when you're fitting Likert scale models that assume ordinal rather than interval measurement, which is almost always the case for these sorts of scales, when you estimate your model in maximum likelihood, you cannot have error covariances. It's not possible. So you have to go this route in terms of introducing additional sources of correlation via factors. So this method factor thing is a very useful technique so long as you can justify the interpretation of what these factors mean. And when your method factors are based on things like, common wording, common stem, it's easier to do that than otherwise. But each of these models, though, adds one term. Right here, one error covariance. Right here, one correlation. Right here, one factor variance because these loadings are fixed to 1. And right here, one factor variance. They are the same. They generate the same predicted covariance matrix. They differ dramatically in interpretation. And this is why I said on the first day, this is not causal modeling. It's just not. There's nothing in the data that can support these different theoretical interpretations just based on this alone. Questions on that? Sure.
The bottom left one. Let's say I did want to look at differences in gender constitution of categories. So then my fifth arm would be the bottom factor, and I would be arguing that that splits into 2 factors of, physical harm to men and physical harm to women.
Yeah, so if you wanted to look at it, though, what you'd want to do is this one right here. Because then you can look at how harm to women predicts things, how harm to men predicts things, and whether harm to men still predicts things after controlling for harm to women. So if you really want to get the pattern of relationship with each of those types, they have to each be represented as factors in the model. If you found a different prediction of harm to women than harm to men on some other outcome, if those didn't function the same, putting them into this higher order factor model would mask that, because there's only going to be one path coming out of the general factor. Whereas if the paths should be different, you wouldn't know that. It would be a distortion. The other thing I'll add is that this higher order factor model on the bottom left really only makes sense if your subfactors are very highly correlated. If they're not, it's hard to argue that there's a common thing that you want to focus on as opposed to focusing on each of the subdimensions specifically. With the formulas that I'm going to give you, yes, although there have been extensions for each of these types of bifactors as well as that for what to do with an omega. It requires some kind of like Schmidt-Lehmann transformation thingy that I'm just not privy to. So I find it less useful though, because you're assuming unidimensionality, and these models are like not unidimensional. So for me it breaks down logically before I even get started on the calculation, but I want to say that in your textbook they give a reference to how to do omega for multidimensional types of models like that. All right, other questions? Okay. So going the other way then, when would you want to simplify the model? So these wouldn't be solutions necessarily to improving fit, meaning that's not guaranteed. So if you have a super high factor correlation, 0.85-ish is commonly a cutoff, although there's no hard and fast rule. If you have two factors that are correlated 0.9, it's hard to argue that you really need both of them. So that would be a situation in which you could either compare your two-factor model to a one-factor model to see if the one factor is not worse, or go back to something that looks like this higher order model so that you get the commonality between them as the thing that you're going to then carry forward to look at relationships with. Dropping items is another strategy sometimes. So when might you drop an item? Well, if its loading is non-significant, you don't need it. It does not measure the factor like you think it does. If the loading is negative, that means it measures it the wrong way. Check your coding or otherwise reconsider that item. Problematic leftover covariances. If you have two items that are super highly correlated, you may not need both of them. If they really get at the same thing, they're not contributing unique information. And rather than addressing that correlation with some extra method factor or error covariance, you might make an argument that you can just get rid of one of the items. And sometimes you will look at the pattern of misfit in the residual correlation matrix and see that one item tends to be responsible for a lot of the misses. That might be an argument to try and get rid of that one item rather than adding in all the patches that it requires to keep it. Tread carefully, though, in that case, because generally speaking, you reduce your reliability once you get rid of items. Now, one thing down here, this is a homework question. This is something I see people screw up in publications and otherwise. Don't do this. Are you all listening? Do you wake up? Okay. If you take out items, you cannot compare model fit with anything based on likelihood. It's not comparable. It's not just not nested, it's flat out not comparable. The reason is that your formula for height is based on the size of your covariance matrix. So if I drop an item, if I go from, say, a 6 by 6 to a 5 by 5, it's going to get smaller because I dropped information, not because I did anything. The covariance matrices are not comparable. So if you change your covariance matrix, you cannot do -2 log likelihood anything. And this is the point at which someone usually says, but in regression you can drop predictors and you can still compare models. That's because here we're not talking about predictors. These are outcomes. That's the difference. The answer key model is different when you have fewer items. So you can't compare back across models. What you can say is that the model that had 6 items did not fit, whereas the model that has 5 does fit. You can talk about the relative merits of each, but you can't do any kind of chi-square comparison between the two. If you want to test whether or not you need an item, the proper way to do that is to leave it in the model but fix its loading to 0. Then you're still back to the same 6 by 6 covariance matrix. The models are comparable, and you're testing the constraint. Whether you made it excuse me, worse. All right. Does that make sense? Good. All right. What else can go wrong? Non-positive definite. When you see that message, it means your model is broken and you can't keep it. Non-positive definite means something went out of balance. It decided that a factor variance or an error variance needed to be negative. It decided that a correlation needed to be greater than 1, or a standardized loading needed to be greater than 1. Its solution that made your data the tallest is improper, is inadmissible. So when you see these words, you've got to stop and try to figure out where the problem is, see if you specified something incorrectly or whether it's just the data. I think that's all I'm going to say about that. So your author in your book suggests an alternative to exploratory factor analysis within a CFA framework where you let all the items load on all the factors and then you can begin to whittle it down. I personally don't think that approach is ever going to lead you to anything helpful, but it is better than doing a straight-up EFA if you really don't have a clue what your factor should be. So we've got global fit, local fit. We're not done yet. Effect size. You have to be able to say that your model makes sense from the perspective of effect size in addition to fit. So I get this question sometimes. One of my first questions I had at Nebraska from another faculty member had fit a CFA model. Fit was nearly perfect. But guess what? Her loadings were non-significant. And she's like, how can that be? Because fit doesn't mean effect size. It's not the same thing. A perfectly fitting model means that your predicted pattern matches the pattern in the data. That the amount of covariance predicted matches what's in the data. It says nothing about whether there's anything in the data worth modeling in the first place. So both of these correlation matrices would be well fit by a single factor model. Even though there basically is no correlation to model on the left side here. Point 1, that would mean a common factor would account for 1% of each item's variance, and it would be 99% not the factor. That'd fit well. It would be meaningless. Another situation in which I see this is in the context of path modeling. Draw another quick picture here. No, I don't want to save that. That is definitely not worth saving. No, there we go. So path modeling is relationships among observed variables only, which is why I'm not talking about that because this class is all about factors. I'll do a couple path model examples just to get us used to doing the same concept in SEM. But I've seen models that look something like this, where we have one arrow there, one arrow there, one there, and one there. So this type of model would probably fit very well because it's only missing a few of the possible arrows that you could put in. Despite the fact that this may fit very well, you could end up with all of these paths being non-significant because the model perfectly reproduces the non-relationships among these variables. That's what that means. So the fact that it fits well is like, who cares? It's like arranging deck chairs on the Titanic. You're going down. So fit is a prerequisite to interpreting the model, but effect size still matters. So effect size in this context is standardized factor loadings. Those are the correlation of each item with the factor. You want those reasonably high. those standardized factor loadings squared become R square. Another piece of the puzzle then is whether or not, even if your model fits, a linear model is plausible. So these are pictures that I made from a factor model with real data. It was a scale in which most of the people picked the lowest answers. So it was some sort of like deviant behavior thing where it's not very common in the population. And the scale itself goes from 1 to 5. So the top plot is what happens when I fit a CFA to the answer to those items. Model fit well. All the loadings were significant, decently sized. But what's the problem here? At a factor score of about 1.5 standard deviations below the mean, we hit the floor. You can't answer 0 or -1 on this scale. This prediction is not plausible. So one option for it is what we're going to do next week, which is to change the model to something that is ordinal instead of interval, and which makes bendy factor lines instead of linear ones. But if you just want to cheat, or you have something that doesn't lend itself to ordinal, so Mayumi, this is for you. This is what your second option would have been, something like this. So you have a scale that goes from 0 to 99 in continuous increments. You can't fit a categorical items model to that. So I had her check to see at what point on the factor scale your item responses that were predicted went out of bounds. And you said that they, at a factor score of +2, it was predicted to be 102 instead of 99. I can live with that. But if you find something that's way out of bounds, this is an option instead. So this is a cheat. This is totally just a cheat. I log transformed the response options from 1 to 5 with the natural log, and then I fit the CFA model. When you back transform, the factor slopes that are linear with respect to the log are exponential with respect to the original item. So I created a bendy prediction line without actually fitting a nonlinear model. And it's not perfect. As you can see, the bottom still starts to head towards 0 here, but it does so to a much lesser extent than it did up here. And as it turned out, the log transformed data, the models fit better. So that's an option for another option for using CFA for data that are not normal, in which a linear prediction is not reasonable. Last but not least, reliability. You remember that alpha sucks, right? If you remember nothing else from this class, you'll remember that probably, and so does the GRE. So let me introduce you to your new friend, Omega. Hello, Omega. It's good to meet you. With 5 minutes left in class. So this comes from your output. Omega uses the factor loadings and the residual variances to compute an index of what your reliability would be if you sum-scored your items. So you're not assuming that all items are equal because you're taking into account their factor loadings and their error variances. You are assuming unidimensionality, though, and that you would have tested through the factor model process. And this last part in the denominator here, that is where you stick in any error covariances. So local independence was the other thing alpha assumed. The errors were uncorrelated. If you have to add some error correlations to make your model fit, they count against you. They lower your reliability. So this is what you would report from a CFA model instead of alpha. You would report omega. So who here likes doing math, like by hand? You do? Okay, well then you can tune me out. For those of you who don't like doing math, or just really get tired of doing it over and over again, here's how to make n plus calculate omega for you. In addition to laziness, the benefit of doing it this way is that you get a standard error. which is sometimes useful to report. So this is a new system of language that we haven't seen yet, in which the things in parentheses are labels. They are user-defined labels that refer to the estimated parameters in each line. So for instance, in my two-factor model, I have labeled the loading for item 2 as L1. I have labeled the second loading as L2, and the last loading as L3. It understands expansion. Here are loadings 4, 5, and 6. Likewise, things in brackets, these are the intercepts. So I've labeled these I1 through 3, 4 through 6. I labeled these E for error variances. I labeled the variances of the factors, the factor covariance, and the means. So I don't need all of these labels, but I put them here for completeness. Then, using the labels, you can make M+ estimate linear combinations of the estimated parameters. So you already know this. If you use SAS, this is an estimate statement. If you use Stata, this is lincom. I'm trying to think, what's it called in R? What is it? Eco?
And the eco combination would be calculated a new estimate in the model.
Okay, yeah, so every software package has the capacity to do this. What's nice about M+ is that you can include variance terms as well, which is why you can do things like genetic models in here. So here's the formula where the factor variances are 1 in this model. The sum of the loadings squared, so an M+ squared is 0.2, star 2, divided by all of that plus the sum of the error variances. So how this works is that you define a new parameter, 8 characters or less, so I'm calling this one omega p, meaning omega reliability for the positive items. It then goes up to your system here and fills in the number that goes with the label. So if item 2, which I'm calling loading 1, if that loading was 0.6, it would fill in 0.6 in my equation here. So it grabs the estimate that corresponds to the label and sticks it in down here. And it does the linear combination, and it uses the delta rule to get a standard error out of it. So in doing that, I get an additional piece of output right here called new and additional parameters. And so my omega for the positive factor is 0.74, and my omega for the negative factor is 0.77. Note that I didn't do omega for the single factor model because it didn't fit. Omega still assumes unidimensionality. It makes no sense to compute it for things that are not unidimensional. But this is what you replace alpha with. We looked at those before. So, how are we doing? Okay, we're almost done with this, but not quite. So we'll pick up the rest of that on Monday. Any other questions before we adjourn? All right, then office hours start now. I will see you all later.